Hey guys, welcome back. This is Jonathan Gardner. We're covering rules for multiplication, which is section 1.3 of Sergey Lang's Basic Mathematics. And in this section, we're going to learn about using logic and theorems and math to solve multiplication problems, or rather, how to avoid multiplying as much as possible. Let's do a quick homework check. Section 1.2 had homework. If you haven't done that homework, I highly encourage you to do it. I gave some hints on how to do that in the end of section 1.1, and if you still have problems solving some of the problems, go ahead and leave a comment below or in the previous video, and I'll try to answer that and get you the help you need. So just like with addition, we're going to start with the basic rules of multiplication, which is commutativity and associativity. So we have AB equals BA. This is commutativity. There's an extra syllable there. And then associativity says ABC is equal to ABC, which is the same as ABC. Okay? We just write it out. All three multiplied together like that. Just with addition, we don't have to be specific about which ones we do first. All right, let's talk a little bit about notation here. So in grade school, you probably learned that you wrote numbers like this. You wrote 5 times 7, right? Well, we're going to use a different notation when we multiply numbers. We'll use dot, okay? And this X symbol will come back in a different form later on. But when we're using letters, if we just write the letters next to each other or next to the parentheses, we know we're multiplying by that. So because we do so much multiplication, that's what we do. All right. Don't really need to talk much about that. I hope you guys are clear. A couple other identities that are important. This is in equations N6. One says if you take 1 and multiply that by any number, that's the same as doing nothing at all to that number. And the other rule says that if you take 0 and multiply it by any number, you get 0 back. These are foundational rules for multiplication. They come up again and again and again and again and again. Let's give an example here. So he has example 2a times 3b. So 2a times 3b. You can write that out this way as 2 times a times 3b. And we're using, again, the associativity rule here. These parentheses, they move, just like they did for addition. In this case, these two parentheses around the 2a are moving to multiply a and the quantity 3b. It's treating the quantity in the parenthesis as a single value. You have to get used to that. If there's a parenthesis, it's a single value. Even though there's something going on the inside, when you do all that work on the inside, you're going to get a number back. So we're taking the parenthesis and moving it to surround a and 3b, just like that. Okay. Next he says, well, let's move that 3 around. So we get 2 times 3a times b. Or we could just write that as 2 times 3 ab, or 6ab. All right. The general rule of thumb, when you're moving factors around, the things you multiply together are called factors. The thing you get out of it is called a product. With addition, the things you add together are called terms, and the thing you get back is called a sum. The general rule of thumb with factors, though, is you want to have the first part always be a number and the second part be the variables. I don't know if you can see that. It's pretty small. You want the number followed by the variable. So just take all the numbers. So there's a 2 and a 3. Multiply them together, you get 6. And then you look at the variables. There's an a, there's a b. So we have ab. Pretty simple. The rule of multiplication and addition together is called distribution. This is distributivity. And it works like this. So you start with some number. I'll scroll up a little bit here. You start with some number, let's say a, and you multiply it by a sum, b and c, and you distribute out that a to each term. This is distributivity. This one is hiding in plain sight oftentimes. Distributivity. Okay. It's hiding in plain sight because when you're going to higher level math, they're going to use this law over and over again and not even talk about it. They're going to pretend like you know. Oh, of course you know you can factor this that way and move these things around that way. So when you're going this direction, we call that distributing. We're taking this A and we're sharing it. We're distributing it to both B and C. You can see there's a common factor there of A. When you go the other way, on the other hand, we call that factorizing. I'm going to use a Z because I'm in America. You people in England and Australia and India can use an S as much as you want. I don't care. I'm not grading your homework. So you do whatever you want. Okay. The other thing that sometimes confuses people is maybe that A appears on the right. And so we get, I should probably write BA plus CA at higher levels of math for numbers that aren't commutative. It'll be important the order you go in. You'll run into that with matrices when we cover that. All right. However, because integers are commutative, these two things are the same, and these two are the same, and those two are the same. And you can even use commutativity for addition, so you get AB or CA plus CA plus BA. You can even reverse the orders of these inside there too. We can prove this theorem here only using this and this. And let me show you how that's done. We start with 0A, and we add A more. And we say what 0A is supposed to equal 0, and of course A is equal to A. Okay. And we say this is actually a 1 here, because 1A is A. And then we notice that there's a common factor of A here. Let's put a 1 there as well. Why not? A of 0 plus 1 is equal to 0 plus A. And what does he do next? 1 plus 0 times A equals 1A equals A. So that's what he proves. Therefore, 0A has to be equal to A, 0. We didn't even have to assume that 0A was 0. We can prove it just by using distributivity. All right? That's good and fun. Similarly, we can also prove that minus 1A is equal to minus A. So we start with minus 1, multiply that times A, and we're going to prove that that's equal to minus A. And the way we do that is we say, well, if we start with minus 1 and we add A to both sides, right? Well, we know that A is just 1A, which is equal to 0. And then we have minus 1 plus 1. We factorize that out. And that gives us 0A equals 0, which is indeed true. Okay? So this is equation N7. N6 was 1A and 0A. N7 is negative 1A is equal to minus A. Notice we say negative 1A, not minus 1A, because this 1 is definitely negative. Okay, in 8, and you probably feel like I'm running through this really fast. I am. This video would be very long otherwise. This is how minus signs distributed with multiplication. This is N8. It says that when you have a minus sign on a product, only one of the factors takes it. The other one ignores it. Okay. Let's do a quick proof. We're trying to show that minus AB is the negative of AB. If they were opposites, then minus AB plus AB would be equal to 0. Remember that from an earlier equation? Using distributivity, we have minus A plus A times B. So we factored out the B. And sure enough, this is 0B. And that is indeed equal to 0, so it checks. Because minus A plus A is 0. Excellent. And N8 and N9. This is, he calls this one n8, and he calls this part n9. So you can do the same to prove n9. Something he emphasizes, and I underlined this in my book, we emphasize that you should be especially careful when working with negative numbers and repeated minus signs. This is one of the most frequent sources of errors when we work with multiplication and addition. And this is definitely true. I make, even having been very good at algebra and calculus and things like that, I still make mistakes with this all the time. So you have to be very careful. Count your minus signs and count your negative numbers. Okay, let's do an example. So we have this complicated equation, or a complicated formula, I guess. I don't know what we'd call it. We have minus 2a times 3b times 4c. And we're going to apply some of the rules that we learned to move multiplying all of those numbers. And then we're going to have a, there's an a here, there's a b, and there's a c. So just like we did with addition, we can just, as long as we don't lose any of the factors, we can reorder them however we like. And of course, minus 2 times 3 is minus 6 times 4 is minus 24. I didn't even tell you how to multiply negative numbers yet. I will tell you. This is what I did. Minus 2 times 3 times 4 is the same as minus 1 times 2 times 3 times 4. This is 24, and so we have minus 1 times 24, and so we have minus 24. That's how I did it. I basically factorized out the minus 1 from one of the terms. I'm sorry. Forget that. This is the same as minus 2 times 3 times 4. Using, I think that was in, oh gosh, which one was that? That was in 8. In 8. So that's what I did. Sorry about that. Count the number of minus signs. If it's an odd number, it's going to be negative. If it's an even number, it's going to be positive. So let's do another one. Minus 4x. Get the paper scrolled up there. All right, so we have minus 4x times 5y times minus 3c is, oh, I ran out of room. This is going to be equal to, we have a minus 4, we have a 5, we have a minus 3, we have an x, we have a y, and we have a c. So we have minus minus, which is positive. 4 times 5 is 20, times 3 is 60. I have to kind of look through my microphone. It's just right there in my face. That's why I like the lapel mic, is it was out of the way, but the recording wasn't that great. I like this microphone better. I hope you guys agree. Let me know in the comments below. Notice minus 1 times minus 1 is equal to what? 1. What does it mean to multiply by a minus, by negative? Right? How do we know this? Well, if minus AB is equal to minus A times B, then minus 1 times minus 1 is the same as minus 1 times minus 1. This is also equal to minus a minus 1. And we've already learned that minus a minus is positive. Excellent. Let's keep rushing through this. Oh, that's N10. N10, let's write that at the top here. If your professor or somebody quizzes you on the equation numbers, this will be useful. I don't think anybody's actually teaching this course. And we have minus A times B is the same as A times minus B is equal to minus AB. And then we have, of course, AB is equal to AB. Okay? So N10 is this equation here. And here is all you need to know about multiplying negative numbers. The rule is same sign, it's positive. Different, it's negative. Okay? That's the rule. Very simple. Because the minus sign doesn't distribute to both terms, both factors, it only distributes to one. So if you have two minus signs, it's positive. If you only have one, it's negative. If you have more than one term, if you have more than two terms, If there's odd minus signs, then it's minus. If there's an even number of minus signs, it's positive. So if you have like 4 or 5 or 6 or 7 terms. I bumped the microphone. Hopefully I didn't give you seasickness or anything like that. So a couple of examples. Minus 3 times minus 5. What does that equal to? Well, we have 2 minus signs. That's an even number, so it's 15. What about 3 times minus 5? That would be minus 15. Negative 15. Pretty simple. All right, let's move on to something far more interesting, and I'm almost out of paper. This is my last piece of paper. I'll have to go get some more. Okay. If we have a times a, we're going to write a to the second power, or a squared. If we have 3 a's, that's a to the third power, or a cubed. If we have 4 a's, that's a to the fourth power, and indeed a times itself n times is a to the nth power. This should remind you of addition. If you have a number plus a number, that's 2 of those. If you have 3 of them, that's 3 of those. If you add it together n times, that's multiplying. Pretty simple, straightforward. What if you have a to the m times a to the n? What does that equal? Well, you're going to have a times a, m times, and then a times a, n times. So that's going to be the same as a to the m plus n. Memorize that. Very important. N11. What if you have a to the m to the nth power? Well, that's basically a to the a times a, m times, a times a, m times, and you're doing that n times. So that's a to the m. That's N12, I believe. Yes. Memorize that. Let's keep going. No, let's not. Let's stop there. Let's do some examples, and then we'll get into binomials. All right, so examples. Let's say we had a squared a cubed. What would that be equal to? That's just a to the 2 plus 3, or a to the 5th power. What if we had, let's kind of see why. So a squared means you have a times a, and a cubed means you have that 3 times. So you have a total of 5 times. Okay. What if you had quantity 4x squared? That's going to be, nope, I did the parentheses in the wrong spot. 4x squared. It's going to be 4x times 4x, or it's going to be 4 times 4 times x, 16x squared. Or, if you like to think about it, 4 squared x squared. That rule is not written out here. Ah, yes. One more rule. A times b to the n is equal to a to the n, b to the n. And he doesn't give that. This is a parenthesis, by the way. It's a terribly drawn parenthesis. You guys should see my working conditions. I'm so oppressed in my office here. All right. And I don't know anything else to do. This is pretty much it. Oh, a cubed to the 4th power. That's going to be a cubed times a cubed times a cubed times a cubed. So that's 3 plus 3 plus 3 plus 3 is just 4 times 3. It means you have 12a, so a to the 12th power. All right, let's continue. Last section here. What happens when you take the square of a plus b? So you have a plus b, and you square that. That's the same as a plus b times a. Apologies for my handwriting there. A plus b. So let's distribute this term, this factor, among those. We get a plus b plus times a plus a times b, a plus b times b. So let me kind of spell out for you the colors here, what's going on. This thing is going here and here. And this thing ends up here. And this thing ends up here. Does that make sense? All right, let's continue. Now let's distribute these guys again. So a times a squared, plus ba, plus b times a, plus b squared. So we're going to write that out as a squared plus, and we have two of these ba terms. We'll write it out as 2ab plus b squared. All right? And we can use similar reasoning for a minus b squared. That'll get you a squared minus 2ab plus b squared. And we can do the same for a plus b times a minus b, which will give you a squared minus b squared. Okay. If you want to follow along in the book, they explain all three of these, but I think this is a good exercise to try on your own. So let's memorize these. A plus b squared equals a squared plus 2ab plus b squared. I could have just written it there. So these are very important. These arise again and again. And in this case, for all of these equations, we call going this direction, we would call that writing it out or expanding. And we would call this factorizing. With the Z, because we're in America. All right. A couple of examples. Oh, that's the wrong color. I want the black. Example 1, they have 2 plus 3x squared. Well, we can use this formula here. So we take the 2 and we square that, so that's 4. Then we take 2 times 2. So this first 2 comes from over here. That 2 goes there. This 2 comes from there, times 3x. And then we finally add 3x squared. The entire 3x, not just 3x squared, but like 3x and 3x again. 4 plus 4 times 3 is 12x plus 9x squared. Or we'd rather write that as 9x squared plus 12x plus 4. Okay. And they have 3 minus 4x. Scroll it up. 3 minus 4x squared, so that's 3 squared. That's that first term there. Minus 2 times 3 from there times 4x. Notice I'm not bringing in negative 4x. I'm bringing in just 4x because the b is 4x. It's not minus 4x. The minus sign here is the minus sign there. Okay. And then we're going to add b squared. So writing that out, we get 9 minus 6 times 4 is 24 plus 16, so 4 squared x squared, which is going to give us 16x squared. Okay. And let's do one more. We have just enough room on this one piece of paper, right? So we have 4a plus 6 times 4a minus 6. So we're going to use this one here. So we take the first terms and square them, and we subtract the second term squared. And I ran out of room there, I didn't realize. So we have 16a squared minus 36, because 6 times 6 is 36. Okay. Now, for the problems, we have, I think you might hear the piano in the background. My kids are playing piano. Even though I asked them kindly, please don't play piano when I'm recording. Okay, so we have this monstrosity here. And this will get a little bit confusing, but follow along. 2x plus 1 times x minus 2 times x plus 5 equals some monstrosity. Okay, how are we going to do this? Well, let's do 2x plus 1 first. So we have 2x plus 1 and x minus 2 next. So we get 2x plus 1. No, let's do it this way. Let's take 2x times x minus 2 plus 1 times x minus 2. So the 2x went here, the 1 went there, and this went with each term. And we factor those guys out, so we have 2x squared minus 4x, because 2x times x is 2x squared, and 2x times 2 is 4x. So then we have an x minus 2, because that's just 1. Okay. Let's take this mess. Let's multiply by x plus 5. So let's write 2x squared minus 4x plus x, that's just minus 3x, minus 2 times x plus 5. So we have 2x squared times x plus 5. We're subtracting 3x times x plus 5. And we're subtracting 2 times x plus 5. And that gives us 2x cubed. There's an x times 2x squared. And then 2x squared times 5 is 10x squared. Minus 3x squared, because 3x times x is x squared. Minus 3x times plus 5 is going to give you minus 15x. And then minus 2 times x, that's minus 2x, and minus 2 times 5 is minus 10. And let's combine like terms, so we only have one x cubed term. We have two x squared terms. 10 minus 3 is 7. And we have two x terms, so minus 15 minus 12, that's minus 17, minus 10. That's how you did that. Okay? That's how you solve that problem. Homework. Let's talk about homework. So, draw a line here, move that up, show my table, it's messy. Okay, so exercises 1. For exercise 1, you're going to produce something that looks like 2 to the m, 3 to the n, a to the r, b to the s. Okay, so let's say I had 24a times 3ab squared times a cubed b to the 5th. So I can expand this 24 into what? 6 times 8. 6 times is 2 times 3, and then 8 is 2 cubed. 2 times 3, 2 times 2 times 2. So 4 times 2, 2 times 2 times 2. This one we're going to get a 3 squared. We have an a squared, and we have a b to the 4th, because it's b squared squared. So 3 squared, a squared, b squared squared. Then we have a to the 3rd to the 5th, that's 15th, and then b to the 5th. Okay, and now when we collect all the terms, we're going to look. So we have a 2, we have 1 2 here, we have 3 more there, so we have 4 2's. For the 3's, we have 1 here, and we have 2 more, so we have 3 3's. For the a's, there's 2 here, there's 15 there, 15 plus 2 is 17, and the b's, 4 plus 5 is 9. That's what we do. That's how you solve that problem, those problems. Okay. For number 2, you are going to start with this first one. So it's going to say expand a plus b to the 3rd power. Now you could start from scratch and find out what a plus b squared is, or you can start with what you already know that's supposed to be. That's supposed to be a squared plus 2ab plus b squared, and then you have one more a plus b. So it's a. So figure that out. And then same for problem 3 when you're doing to the 4th power. Start with the ones to the 3rd power. You'll find a pattern. It'll be beautiful. Problems 4 through 7 is 4 through 29. Just remember those 3 expansions. Remember that a plus b squared equals a squared plus 2ab plus b squared, etc. And try to fit it into those patterns. So look for something plus something and then something minus the same thing. Okay, that's one of the patterns. Another pattern is something minus something squared, and the 3rd pattern is something plus something squared. And use the formulas. Don't do these by hand if you can avoid it. Some of them you do have to do by hand. That's okay, like we did for that last part. Like remember when we just did this? So for those problems, follow the same pattern I used here, where you distribute the entire term to the individual terms. And for problems 30 to 33, this is how it works. So if we had every 10 years, we had 5 times the population. And we started in 1910. with, let's say, 100,000 people, right? Well, in 1920, that's 10 years, so we're going to have 5 times. In 1930 is 10 more years, so we're going to have 5 times 5 times. So that's 25 times. Or 5 squared times, right? In 1940, another 5 years passes, so we have 5 times 5 times 5, or 5 cubed. You see the pattern? Okay, so this one would be 500,000. This one would be 2,500,000. This one would be 125,000, or 12.5 million. That's how it would work. All right, I hope you enjoyed those homework problems. Let me know how you do. If you have any questions, be sure to comment below. And you guys have a great day. Take care. Bye-bye. Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's Basic Mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.